dear all, now in this lecture we will be solving a differential equation using only power series. Well, in order to do this, we're gonna have to write each power series for the y, y prime, and y double prime, as I did down here. We're gonna plug all of these series into our differential equation, so we're gonna get rid of the y's, and we're just gonna have an equation with series into it. And we're going to set it equal to 0 because we're just substituting into our differential equation. Finally, we're going to combine these series, and then to set this equal to 0, we're going to make sure the left-hand side also equals to 0. And this means that we're going to most likely have some constants in front of it and a series. And the constants and the series must be equal to 0 so that we will get this 0 out of this solution, so it will work. And then this will give us the recurrence relationship, and we're gonna find the first few terms of this series solution. Okay, so this differential equation looks something like this. So we had y double prime plus xy prime plus y equals to 0. So I just rewrote everything in terms of their series notations. Okay, and now our goal is to combine these series. The first thing we want to be doing is make sure the exponents of x are matching. And obviously they are not, but in this case we have an x in front of the series, so we can actually kind of carry this into the series. So this second series will become n equals 1 to infinity of a sub n times x to the n power. Okay? Plus, and we have this second series n equals 0 to infinity a sub n x to the n equals 0, and we have the first series as well. However, if you can notice, this series exponent for x is not equal to n. Okay, this is an n minus 2. So we want to adjust that accordingly so that we can make operations off of all of these work. Okay. So what we can do here is basically, from the trick I showed you guys, we can subtract 2 from the index, and then we will be adding 2 for each n we see there. So we would substitute n plus 2 to make sure that we get x to the n power. So why don't we just start with that? So we're gonna say n equals 0 to infinity. Okay, I'm subtracting 2 from the index, so I'm gonna have to add 8 sub n plus 2 times n plus 2 times n plus 1 x to the n. Okay, plus sigma n equals 1 to infinity a sub n times x to the n plus sigma n equals 0 to infinity a sub n x to the n equals 0. Awesome. Right now, all of our exponents are matching, which is a really good news, which is really good. We want this. But the only problem is the series indexes don't match, right? We have different indexes for a series. So we can solve this problem by getting the first term for the first and the third series so that all of the indexes would match 1. Okay, that seems to be the only way to do this problem. So we're going to write out the first term of the first and the third series. So if we substitute n equals to 0 into this series, we're going to have a sub 2 times 1 times 1. So I'm going to have 2a sub 2 here. That's it. Okay. Plus, we're not going to do anything with that. And I'm just going to skip the series for now, just to get the constants out to make it look better. So on the rightmost series, we're going to get another first term. And if we substitute n equals 0, we're going to get a sub 0 times 1. So we're going to get a sub 0. And now we can write all of our series together. Okay, so our first series was a sub n plus 2, n plus 2, n plus 1, x to the n, plus the second one is n equals 1 to infinity, a sub n times x to the n, plus this third one is going to be n equals 1 to infinity, a sub n x to the n. Okay, and this is all equal to 0. Well, finally, we can rewrite this. Okay, we cannot obviously combine the constants, but what we can do is we can combine these series into a single series. Okay, so our series will become a sigma n equals 1 to infinity. So we're gonna imagine you pull out an x to the n power and adding everything else here. Okay, so x to the n power times a sub n plus 2 times n plus 2 times n plus 1 plus a sub n times n plus a sub n. Okay, and this is going to be equal to 0. Okay, this is really important for us. Okay, so what can we do with this now? You might ask. Well, we know that in order for this series to be equal to 0, we cannot get something negative out of a summation, okay? We always keep adding on summations, and the numbers are positive because n is already defined from 1, so we're going to get a positive series. So what we can do is make sure the inside is going to be equal to 0. Well, x to the n power is never going to be equal to 0, right? I mean, you can plug any number you want for n, and you're always going to get a positive or, yeah, a positive number. You cannot get 0. So the first statement we can draw is that this whole chunk will be equal to 0. And the second statement is this chunk will be equal to 0. Okay? And these two chunks will help us build our recurrence relationship. And based on that relationship, we're going to write the first few terms of the series. Okay, so for step 1, we should say that 2a2 plus a0 equals to 0. And because this is equal to 0, we can write this in terms of a0, and a2 must be equal to negative a0 over 2. This is the first statement, okay? The second statement is what we want is that this inside should be equal to 0 as well, okay? So just keep this in mind that this has to be working, okay? a2 must have a relationship with a0 such as this fraction. And for this chunk, what we can do is we're gonna factor a sub n here, do some algebra, and get a sub n times n plus 1, okay? Plus, you cannot factor for a sub n plus 2, so we're gonna say a sub n plus 2 times n plus 2, n plus 1 equals to 0, okay? And then we're gonna carry this guy out to the right-hand side, so we're gonna have a sub n, negative a sub n, n plus 1 equals to a sub n plus 2, n plus 2, n plus 1. And these n plus 1s cancel each other out. And finally, our final relationship, our second recursive relationship will be a sub n, negative a sub n equals to, you know what, actually, why don't we do this? We want to write in terms of the big term, okay? The bigger a term would be more convenient. So a sub n plus 2 is equal to negative a sub n divided by n plus 2. Okay, so we have these two relationships. We know the first term of this relationship and another term of this relationship. And we can confirm. Plug n equals 0. What happens? If you plug n equals 0, you're going to get a sub 2 equals to negative a sub 0 over 2, which does match the first given condition. So this is good. This means that what we're doing is working. So what you want to do is build a few terms here, okay, using this formula we just generated. So I'm going to build a few terms. Can we start from a sub, yeah, we cannot start with negative 1 because we would have a negative 1 there. So we can just keep going from 3. So a sub 3 will be equal to what? A sub 3 will be equal to negative a sub 1 over 3. Okay? And then a sub 1 and a sub 0 will be our base variables, our variables we're going to use are free variables. Actually, more of a constant. Think about like a C1 and C2 in previous differential equations. We're going to have these are just going to be our C1 and C2. So A4 should be equal to what? Well, you're going to say n equals to 2, so you're going to get a sub n, negative a sub 2 over 4. And negative a sub 2 is just going to be a sub 0 over 2, but you're going to have an over 4 too, so you're going to say a sub 0 over 8. Okay? And let's say a sub 5 and wrap it up, because we can keep going all day doing this. You don't have to generate all the terms. You're not expected to do that. You're just expected to be able to generate the first few terms, which we're pretty much done with. So a sub 5 will be a sub negative a sub 3 over 5, and you can rewrite this as a sub 1 over 15. Okay, a sub 1 over 15. Now that we have gathered our constants, let's build our solution. So we previously defined that our solution is equal to y, and y is equal to n from 0 to infinity, a sub n, x to the n power. Let's get the first few terms out of the way. So we want a sub 0 plus a sub 1, x to the 1, plus a sub 2, x to the 2, plus a sub 3, x to the 3, and so on. Okay, you can kind of see where it goes. Every a n term gets an x n term associated with it. So let's write it down. Let's get our... So the best way to do this is kind of separate the odd terms with even terms, so that we would make our life a lot more easier. So let's start with the terms we have generated. Okay, we know a2, a0, and a4. Okay, so a0 is a0, so we're just going to write that down, plus, and the second term is a2 times x squared. Well, x squared is just going to stay there, but a2 is negative a0 over 2. So we're going to have negative a0 over 2 times x squared. And now we can write a4. Okay, so a4 times x to the 4 is our next term, and a4 is a0 over 8. So we're going to have a0 over 8 times x to the 4th. And our series will keep going on like this. Alright, well, it's really nice if we can simplify this. So we can just pull out an a sub 0 out, and we're going to have 1 minus x squared over 2 plus x, plus that plus looked like an x, plus x to the 4th over 8 plus, and it goes on and on and on. Okay, so this is our even terms. This is a solution for even terms. Now let's make one for odd terms. So we have a1x1. So a1x1 will be there, a1x1 plus a3x3. So I want to go ahead and find what a3 was. a3 was negative a1 over 3. So we're going to have negative a1 over 3x cubed. And now we have a5, and a5 was a1 over 15. So we're going to have a1 over 15 x to the 5th power. And it will keep going. Okay. Well, this is odd terms. Okay, and for the odd terms, we can just pull out this. Likewise, we can just pull out an a1 here, and we would have x1 plus, actually minus, x cubed over 3 plus x to the 5th over 15 plus dot dot dot. The first three terms are enough. And this is our solution. So basically we have the even terms, a0 times 1 minus x squared over 2 plus x to the 4th over 8, and it keeps going, and the odd terms. And you might ask, hey, what is this a0 and a1? Well, remember how we did differential equations with second order differential equations? We had like c1 and c2. Remember? That's just c1 and c2. It's just another constant. Because this differential equation, we didn't have an initial condition. So if you don't have an initial condition, your differential equation could be anywhere on the horizontal vertical axis, right? We could draw a slope field for this, but we couldn't give you an exact particular solution because you didn't give me a starting point. You didn't give me a initial value. So this is why a0 and a1 will remain there as constant numbers.